morning. Welcome to the third day of the CQIQC workshop. So this morning, we have a long day today, and we are going to start on time. So the first speaker is Marcel Franz from UBC, and then he will tell us about a very interesting thing called d-mon. Thank you.
Okay, good morning. Let me first thank the organizers for inviting me to this conference. I usually don't come to quantum information conferences. My background is in correlated quantum matter, mostly electrons, topology, and superconductivity. But recently we made a foray to qubits, and so I assume this might be the reason why I'm invited here. So d-mon, what is d-mon? Well, let me just tell you, it's a proposal for a new type of a qubit that we view as an improved transmon qubit. And when we submitted a manuscript or the manuscript to the archive with this name, it was the first time in history when it got held up. So it didn't appear next day. And we got this cryptic message that it's been sequestered for a review by archive administrators, and that never happened to me in my 25-year history of submitting many papers to the archive. So I think there's been lots of submissions with a d-mon in their title, but eventually somebody looked at the paper and decided it was legit. So it is now actually published. So okay, and it worked. And it's working now. Okay, so motivation. I'm going to talk about, or the proposed new qubit design is based on twisted materials. So in a way of motivation, maybe most of you, or some of you at least, heard about twisted quantum materials, which has been the biggest thing in quantum materials in the past 5 or 6 years. And perhaps the most progress on this front has been gained on twisted bilayer graphene. It all started with this paper from Pablo Jarillo Herrera's group at MIT that I'm citing here, who reported for the first time a successful creation of twisted bilayer graphene. So let me motivate what I'm going to say with that. So graphene itself is a monolayer thin sheet of carbon atoms arranged in a simple honeycomb lattice. And what these guys did at MIT, they took 2 such sheets and assembled them on top of one another with a tiny twist, as shown here in this picture. So if you squint your eyes, what you can see is this modulation where the twisted material looks different here than it looks in here. And you can see a periodicity on a scale that is much longer than the native carbon-carbon distance in actual monolayer graphene. This is the so-called moire structure that obtains anytime you twist 2 periodic structures on top of one another. And this has been a huge breakthrough because for basically all its history, we condensed matter physicists have been shackled by this fact that periodicity of the potential in which electrons move in solids is set by interatomic distance, which is invariably on the order of a couple angstroms, right? Like it's in this graphene lattice. However, when you create this moire potential, you can see here in this example that the period can be much larger. So for the first time, we've been able to experimentally see the consequences of what happens when this periodicity is changed dramatically, like for instance here. And in the 5 years following this 2018 discovery, many groups jumped on this, created these twisted structures, probed them in many different ways, and this has been a true bonanza of new information. New properties of solids never before seen have been observed. People have seen new phases of matter, including integer and fractional Chern insulators, quantum spin Hall insulators, unconventional superconductors, and this is all ongoing. So this has been one of the most fruitful new directions in condensed matter physics that I have ever witnessed. Now, what I'm going to tell you about today is a story of another twisted material, which is a kind of new kid on the block. And this is a twisted high TC cuprate superconductor. And this is the content of my talk. I will give you a very brief review of the cuprate bilayer theory. Then I will show you some experimental evidence for the effects that were predicted. And then I will spend the rest of the time describing the proposed application of this physics for an improved transmon qubit. So that's the plan. The work that motivated us to think about twisted high TC cuprates is this paper here, published in 2019 by Yang-Bo Zheng's group in China, where for the first time in more than 30 years of history of high TC field, they were able to isolate a monolayer, single monolayer of high TC cuprate visco. It's this compound, one of the prominent examples of the cuprate family with the critical temperature near 90 Kelvin. And this has been a difficult journey for technical reasons that I don't have time to discuss, but only in 2019, this was the first group to succeed to look at a single monolayer of this material. And what they showed in particular is that a single monolayer has the same critical temperature as a bulk crystal to within 1%. Okay, and this was not really known before. People conjecture that high TC is a property of a single monolayer of this material, but this was not known until basically a few years ago, and that's why this was an important discovery. So as soon as we saw this, we started thinking, okay, people twist graphene, they twist all sorts of other materials. Now we have a monolayer thin high TC cuprate. So is there anything interesting that one can do when twisting these materials? This is just to show here a picture from Yang-Bo Zheng's paper, where they demonstrated that all the properties that were previously observed in bulk crystals actually translate to a single monolayer. So again, if I had more time, I can describe these pictures, but this is a story for a longer talk. So here's, without ado, I jumped into the main idea of this twisted cuprate, and there's other interesting physics that I will not have time to talk about, but just one aspect to give you an example what is new when you start twisting materials. So there's many things about cuprates that we still do not understand after more than 30 years of vigorous research effort. One thing that we do is that these are D-wave superconductors. What this means is that the superconducting order parameter, that is the symmetry of the Cooper pair wave function, is different than all other conventional superconductors in that it has this D-wave symmetry illustrated here. So just like a D-wave orbital in atomic or molecular physics, when you take a Cooper pair wave function and you rotate it by 90 degrees, it changes sign. So that's the meaning of this little flower, which is meant to represent the two lobes, positive and negative, of this D-wave order parameter. Okay, so the idea is this: take a monolayer of this D-wave superconductor represented by this visco, for instance, that has been exfoliated to a monolayer limit, then take another one, rotated by, in this case, large twist angle, 45 degrees, make a bilayer structure, and then investigate what happens. Now, what you notice, the way I drew these D-wave orbitals, they are now rotated by 45 degrees, which means that they are, I would say, fully frustrated. Specifically, the two wave functions of this D-wave type are now frustrated in a sense that a Cooper pair cannot tunnel easily between the two layers because those two wave functions are now orthogonal. The prediction based on this idea is that the system resolves this frustration that we forced upon it by this rotation by spontaneously breaking time reversal symmetry and forming this exotic, what we call D plus ID combined superconductor. And I will unpack for you what this means. And this is going to be crucial in the discussion of the qubit that I will present later. So what's interesting about this and why I mentioned it's an exotic superconductor, its properties have been studied theoretically before, although there's never been an example in actual experimental physics of this. It is known that it's a fully gapped superconductor in the bulk, but it's topological. What this means is that if you were to put such a d plus ID superconductor on a long strip in the bulk, you would find a fully gapped spectrum, just like in lead or aluminum or other superconductor, but it would have these topologically protected edge modes that propagate in a chiral fashion around the edges. So for instance, on this edge, I have arrow pointing this way, meaning the edge mode moves in one direction, and on the other side, it moves in the opposite direction. And these are protected by the bulk topology because this has a non-zero Chern number, specifically plus or minus 2, depending on which of these two time reversal symmetry broken phases is realized. I will not do much math here today. It's early morning, but one can actually understand with a very simple math why this happens. So I will go through that and then leave you in peace in terms of equations. So the easiest way to understand the origin of this time reversal symmetry breaking is to look at the free energy, Ginzburg-Landau free energy of these two superconductors. And it's actually quite simple. So one can write it like this. The two layers are described by two complex scalar order parameters that are called psi1 and psi2. There's some free energy associated with each individual layer, which I call F naught. And then there's three possible terms that you can write, A, B, and C, that couple these layers to fourth order, as we usually do in these calculations. Now, the important terms here will be these on the second line, B and C, because they are sensitive to the relative phase of the two order parameters. As I mentioned, they are complex fields. The only thing one has to remember is that because these are D-wave order parameters, that places a constraint on this coefficient B, namely, it depends on the twist angle theta in this fashion. Namely, it expresses this fact that when you rotate one orbital by 90 degrees, it changes sign. And that's reflected directly in this angular dependence of the coefficient B. Namely, at 45-degree twist, it has to vanish. And that's a symmetry statement that's non-negotiable. Okay, so we can actually solve this problem assuming that the two layers are identical. I will assume that the two order parameters have the same amplitude, but they can differ by their phase. I just substitute this ansatz into the free energy, and I get this free energy here marked in red, which one can think of as a Josephson free energy for this bilayer system. Now, it looks kind of maybe complicated, but as a function of this relative phase between the two layers, there's only two terms, cosine phi, which is the usual Josephson tunneling term, and it expresses the fact that a single Cooper pair can tunnel between the two layers. And then this cosine 2 phi term is a second order Josephson term, which expresses the fact that two Cooper pairs can tunnel coherently at the same time. Now, normally, this second term is neglected in discussions of ordinary Josephson effect. However, in this case, it will become important precisely because these are D-wave superconductors, and near 45-degree twist, the prefactor of this first leading Josephson term will go to 0, so the physics will be controlled by this second term. And it's almost a high school level analysis to analyze or to find the minima of these free energy as a function of the angle. And it looks like this. I plotted this free energy here in various colors blue represents small twist angles. And as you would expect, at small twist angles, there's only single minimum at phi equals 0. That means the two layers want to be in phase. That's the lowest energy state. However, as you increase twist, at some point there's a critical twist angle at which you find that there is suddenly two minima at non-zero phase phi. And that's the signal for time reversal symmetry breaking. The system has to choose which of these two phases it will go to, just like, for instance, a magnet has to choose whether its magnetization is up or down, and the two states are then conjugate under time reversal symmetry. So this is the simple idea why one expects this time reversal symmetry breaking to occur. One can map out from this the phase diagram of the system, which I've done for you here. So the horizontal axis is a twist angle here from 0 to pi over 2, and the vertical axis is temperature. And you can see that this time reversal broken phase occurs in this wedge here, centered around 45-degree twist. And interestingly, at exactly 45 degrees, the theory predicts that this time reversal broken phase persists all the way up to native critical temperature of the monolayer, which is 90 Kelvin, say, in BISCO. So potentially, this theory predicts that we have this topological superconductor up to a high temperature. And you know, once we first saw this, we thought, oh, well, this actually is interesting. Now, I mentioned this is a topological superconductor. How do we see that? One can write down a more microscopic theory, which I will not do here, calculate the Chern number, and find that is non-zero. But more visually, one can look within this simple BCS microscopic theory. One can look at the spectral function. And what I'm doing here, I'm parking the parameters such that I'm in this time reversal symmetry broken phase. And I'm putting the system on a long strip. And this is the spectral function of electrons inside in the bulk of this strip, away from the edges. And what this tells me is that I have a fully gapped spectrum, right? There's no states near omega equals 0. And that tells me I have no low-lying excitations in the system. However, I can calculate the same spectral function at the edge of the sample, just looking at the edge. And I see that now that gap is traversed by these right-moving edge modes. And these are the protected edge modes that I mentioned previously, which show me directly that this is a topological phase. In this case, I have 4 different edge modes, meaning I have Chern number 4. And again, one understands that from microscopic calculation. These edge modes technically are Majorana. So you know, if you're interested in Majorana fermions, there's an example of a Majorana edge mode. Okay, so that much about the theory. Now, some experiment. I gave a first talk on this back in the pandemic. It was 2020, still everything was shut down. I give it on Zoom remotely at some conference. And then very next day, I get a phone call from Philip Kim from Harvard, who was not at the talk, but somebody told him about the talk. And Philip tells me excitedly, we are doing that experiment that you're thinking about. And he sent me this picture. So what they are doing, these flakes here, they are BISCO flakes. And you can see one of their devices where they basically take a single flake, they exfoliate it, they cleave it, twist it, put it back, and here's the twisted portion. You can see those 2 flakes at, in this case, close to 90-degree angle. Then they put some electrodes and measure transport through that twisted region. So they were doing this experiment. People have done this kind of experiment before, but didn't see anything interesting, presumably because the interfaces were not clean enough. Here's a TEM transmission electron microscope image of that interface here. And what Philip told me then is that it's atomically perfect. All the way to the interface, atoms are arranged with no defects compared to some less clean damaged surfaces, and this is crucial to see some of these effects that we predicted. So they observed all sorts of interesting things that, again, for non-superconductivity experts maybe are not that important. Here's one example of this. So for the first time, they measure the critical current of these twisted junctions as a function of twist, and they see for the first time a strong suppression of the junction critical current near 45 degrees, which is this characteristic of a D-wave superconductor. I mentioned at the beginning that these Cooper pairs at 45-degree twist cannot tunnel, and that's the experimental verification of that. Interestingly, in earlier experiments, this was not seen. Earlier experiments have seen basically no suppression and interpreted this as evidence for ordinary S-wave superconductivity, or basically we're not able to interpret that. So for the first time with these clean interfaces, they are able to see this basic property of high TC cuprates. There's some other interesting features of a temperature dependence, which again, I will skip, but the first question I asked Philip in that conversation was, do you have any evidence for this time reversal symmetry breaking near 45 degrees that we predict? And at the time he told me, well, I don't know, I have to check. And very quickly he came back with this plot. This is something called Shapiro steps. And again, this is a standard way to measure the response of a Josephson junction. But if you never heard of Shapiro steps, then I'm not going to explain it right now. Basically, you see these bands, which are bands as a function of voltage that you apply to your Josephson junction, and they are scaled in terms of frequency that you feed into the junction, microwave frequency. And they are in units of h bar over 2e, where e is a charge of electron. And basically, these bands at integer values of that voltage tells you that what's tunneling through the junction is an object with charge 2e, okay, Cooper pair. And this is seen in all superconductors. Now, what Philip pointed out to me is that in addition to those prominent steps, they also see half integer steps here that you can probably see. And if you interpret those within the same theory, they tell you that it's 4 E objects that are tunneling, meaning 2 Cooper pairs at the same time. So this they only saw in these 45-degree twisted junctions, not in any other angles. And it can be interpreted as a significant component of the second order tunneling, which is required for this time reversal symmetry breaking. We modeled that again using this same Ginzburg-Landau theory, and indeed within the model, again, this doesn't show unfortunately so well, but we see these half integer Shapiro steps. Now, perhaps more tellingly, they reported a little later so-called Josephson diode effect, which is a direct probe of time reversal symmetry breaking. So again, very quickly, what is Josephson diode effect? You have a Josephson junction, which is shown here. And normally, you would expect that it's a reciprocal device, that the current, whether it flows up or down, as indicated by those arrows, the characteristic of the junction should not depend on that. When that's not the case, when the junction is non-reciprocal, that's called Josephson diode effect. And this is something that came to prominence recently. And Philip reported that they see it in their twisted cuprate junctions, but again, only close to 45 degrees. Okay. Now, why is this important? It is important because it's very easy to see that the absolute symmetry requirement for this non-reciprocal effect is that time reversal symmetry in your device is broken. It's a very simple proof that has 2 lines, which says that if the time reversal symmetry is respected, then the current has to be reciprocal in this type of a situation. You can use this non-reciprocity to do this cool rectification experiment when you apply a series of pulses to your junction in current, and then you see voltage only on the positive side. So it really behaves like a diode. So this is a kind of very strong indication that in these junctions, time reversal symmetry is broken, and paper with these results has recently been published. So indeed, these twisted cuprate junctions actually realize probably this high temperature topological superconductor, although so far we only have evidence for time reversal symmetry breaking. We don't have any direct evidence for that topology. One would have to see those edge modes experimentally, which is a harder experiment, but this is something that people are working on. Okay, so I have still, I hope, 5 minutes. So 10 minutes, sorry. Good. So I will discuss the proposed qubit design based on these ideas. Transmons have been mentioned a few times in these series. So I just repeat that they are the preferred qubit that now powers all the leading quantum computers, including IBM, Google, Rigetti, and so on. So very, very important device. How does transmon work? So basically, the important part of transmon, which is based on this 2007 theoretical paper by Koch and coworkers, the heart of the transmon is this part here. It's basically a Josephson junction in parallel with a capacitor. This is realized here with 2 Josephson junctions and flux, which allows one to actually tune the effective Josephson coupling. But in principle, one just needs 1 Josephson junction. And this was designed to overcome the so-called offset charge problem that plagued earlier versions of superconducting qubits, for instance, the Cooper pair box. And let me explain what this offset charge problem was, because that's going to be important for my discussion here. So you can write down the Schrödinger equation for the transmon qubit. This is, again, a well-known equation coming back to this paper or even papers before that. The first term here is the charging energy, and M is an operator that represents the number of Cooper pairs on your Josephson junction. Phi is the Josephson phase, and so you have basically the kinetic energy here and the potential energy, and this acts on some wave function that is wave function of the phase. Importantly, there's this Ng factor, which is basically some unknown offset charge that exists on your physical device and is not easy to control in practical terms. It depends on electrostatic environment of your junction. And moreover, not only you don't know how to control it, but experimentally it is seen to slowly fluctuate as a function of time. And this is a problem, or has been a problem, in these early designs, like a Cooper pair box, for the reason that I explained. So when you solve this, this transmon Schrödinger equation, just recalling that the number operator is canonically conjugate to the phase, so that I can write it as d over d phi. You can solve this equation, and actually even analytic solutions exist, but one can solve it numerically. Either way, it's easy. The early devices worked in this limit where the charging energy was roughly the same as the Josephson energy. And when you solve this equation for its eigenvalues and plot those eigenvalues as a function of this offset charge Ng, you see that there are large variations, right? And you can see that this is not a good news, because if you want to use these 2 lowest energy levels as working levels of your qubit, then this offset charge fluctuates slowly in time. The frequency of your qubit will vary as a function of time, and that's not good because you don't know how to address your qubit. So what these authors in 2007 paper proposed is that if you instead go to what we now know as a transmon limit, when this EJ, the Josephson energy, is much larger than the capacitive energy, then this problem starts going away. For instance, when this ratio here is, say, 50, you can see that these energy levels start being completely independent of this offset charge. So even though the offset charge might fluctuate as a function of time, your qubit is then stable. So that's how this problem has been solved. And indeed, all, as I mentioned, working qubits these days, almost all of them work on this principle. It has one drawback, and it is that if you look at this spectrum, it's now becoming nearly harmonic, meaning these levels are almost equally spaced, not quite, but almost. So why is that bad? Well, this is not good because when you want to manipulate these two levels by sending microwave pulses, unless you send very well-defined pulses with a very well-defined frequency, you run a risk always to exciting into the second excited state. And in a quantum computation, that's basically a catastrophe because your qubit is out of your logical space and the calculation has ended. So basically, this weak anharmonicity is a problem or something that limits the speed at which you can operate transmon qubits. Okay, so this is the issue that this proposed new transmon can actually solve, and let me explain how we propose to solve it. So instead of using aluminum, we propose to use actually a D-wave superconductor. And there's several different designs, but the simplest is to put a flake of D-wave superconductor on a conventional S-wave superconductor. What happens, you can write down the same free energy, and again, by symmetry, you conclude that direct tunneling of Cooper pairs, this first order term, is prohibited by symmetry, and the leading term is this co-tunneling, as in 45-degree twisted bilayers. And so you have a free energy that to leading order has a cosine 2 phi rather than cosine phi behavior. Okay. Now I will, on the next slide, try to convince you that that's a crucial difference for the operation of such a qubit. I can write down the same transmon equation. The only change is this factor of 2, and you may think, okay, that's a trivial change. How does that do anything? So it actually does a great deal. And here is how one can understand what's happening. So now my potential is cosine 2 phi, so it looks like this. Instead of just one well, I have two. At low energies, I can approximate these by harmonic potentials. And to that first approximation, I just have equally spaced levels down here. Okay. But now, these, say, if I look at the ground state wave function, it will have some extent. And two ground state wave functions will have a small overlap. And you know how you treat them. You can treat them in perturbation theory. This overlap will result in a small splitting. So the level spacing will look something like this for this cosine 2 phi. Okay, and right away from this simple argument, you can see that this will not have a problem of weak anharmonicity, right? Because there is these two levels could be split very little, and the splitting to the next two levels is controlled by some other physics. Okay, so that's the idea. And of course, we have to validate this. We have to solve this transmon equation in more detail, and that's what we did. But basically, this is the idea. So basically, if we can show that this kind of design still remains insensitive to this offset charge problem, then we're good to go. And indeed, this is what we did. Just as a side, I mentioned before that a practical transmon actually has two Josephson junctions with some flux in the middle, so that they can control the effective Josephson coupling. In the same way, one can do, it's called a split transmon design. One can do split d-mon design. And again, I'd be happy to answer questions about this, but one can do that, in which case one can control some parameters of that circuit. Basically, what happens with this split d-mon design is that you get additional term here, which is cosine phi minus this external flux that you drive, and that gives you some parameters that you can tune externally. And then you can solve this transmon equation for this kind of split transmon or d-mon geometry. And I don't want to go to details. There's a lot to unpack, but basically there's various parameter ranges that you can put this in. And in most of them, the spectrum as a function of this offset charge looks something like this. And you can see right away that generically you get two features. First, there's this insensitivity to the offset charge. Again, this is the same as transmon, but for most of these parameters, you find that there is a tunable and potentially large unharmonicity. So for instance, in this graph, you see that the unharmonicity is large. In this case, it's positive because the spacing between the level 1 and 2 is larger than 0 and 1. In this case, it can be negative, which can have some advantages for practical qubit design. And one can map out these parameters and find sweet spots where you optimize this flatness and you optimize the unharmonicity. And so one has all this flexibility. So potentially, if we can convince anybody to make transmon not from aluminum, which is the material of choice, but using high TC cuprate, it has all these advantages. Of course, there's other properties of cuprates that may not be so great for qubits, but they have high transition temperature, they have large gaps. So this is something that perhaps would be fruitful to investigate. Let me point out that in parallel with our paper, and this is my last slide, a group in Europe proposed what they call flower-mon qubit, where they go back basically to twisted D-wave flake geometry. It has very similar properties. This is actually a combination of experimental theory paper, and this group, as I learned later, actually now have funding and are working on this in their lab. So I'd like to thank you for your attention, and I just put up my summary slide. Thank you.
Thank you for the talk, by myself.